This next session is our software discussion and panel. We're very fortunate because we have really experts in their field. And if you're unfamiliar with this process, we provide them a technical issue, usually a real-life problem, and in this case it is a real-life problem. And they can use their very sophisticated tools to give us feedback and help us understand the problem. I mean, this is a vital part of what we do. I'm Tim Siegel, I'm your moderator. We have Gary Gregory, PhD, Dr. Gary Gregory, who will talk about some limited equilibrium analysis. We've got Augusto Lucarelli with Itasca, who will be talking about the use of FLAC. And then we've got Jeff Lamb with Rock Science that is going to be, and Sina, I'm sorry, I didn't mean to drop you off, that from Rock Science that will be talking about their suite of software in analyzing this problem. A little introduction. This is an embankment in West Virginia. It was constructed in association with a fairly large bridge, as you see here. I need to acknowledge the folks that worked on this problem for Dan Brown Associates, and that the lead person was Mark Madgett. Taylor Day, who was here yesterday, worked on it. He's since left our firm and gone with another firm in the local area. Isaac Heldes worked on that, as well as John Turner. For us, I felt that we needed to acknowledge them. A couple of points about this problem. We were very specific, and again, our organizers, and particularly Jeff Seeger, and had pointed out he wanted them to look at things like frame action in the system that we had proposed, which was a micropile insert type system. Comment on the batter angle and its effect on the design and performance of the micropiles, and then talk about how the forces from the micropiles get into the cap. Very briefly, here's some of the data that they got to look at so that you kind of know some of the basis. This embankment, as I said, was built in accordance while the bridge was also being constructed, and thereafter they began to see the fill slide, and you can see here that the fill is underlain by colluvium, which is underlain by rock, and that the inclinometers showed that the failure surface was within the colluvium. And if you're familiar with West Virginia, colluvium is not uncommon. When we looked at piezometer data within the colluvium, we saw that it was fairly constant over time. In most of the layers, we did see some slight variation at some points, particularly within the colluvium. But we had some piezometers in the fill and colluvium. And then just to give you an outline of the design, it was, like I said, kind of this micropile frame with a cap beam, and they were embedded into rock. And with that, I believe, oh, and I will add to that, we also considered some other solutions, and this one looks, after Mike's talk this morning, we did consider an anchor block system, but again, that was jettisoned to look particularly at the micropile and cap beam. This is a quick look at the final design, and this is what our panelists have been asked to look at. It was an alternating micropile design, as they were every other pile was battered in the same direction up and down the cap beam. Are you ready to go? All right, so I will introduce our first speaker. It'll be Gary Gregory. Take it over. I think.
Yeah, there we go. All right, thank you for attending. see. There we go. Okay, the analysis included in my presentation were performed with my slope stability analysis program, limit equilibrium program, 2D and simplified 3D, and Plaxis 2D finite element method software. It was developed by Plaxis BV, as you probably know, and it's now part of the Bentley Systems, Inc. And as Tim pointed out, the example consists of stabilization of a landslide with A-frame micropiles. So there's some analysis notes that I want to mention at first. Factors of safety are expressed to 3 decimal places to facilitate the comparison among the various analyses. That does not imply that they're accurate to 3 decimal places. In fact, you may have heard Mike Duncan make this statement, and he attributes it to Jim Mitchell, that your credibility is inversely proportional to the number of decimal places in your factor of safety calculation. And it's so true. But there are 3 places just so we can compare among the various analyses. Also, due to the complex nature of the example, there's some simplifying assumptions that had to be made. Okay, this is the geometry of the slide of the problem as presented to us. And the plans for the construction plan show a right facing slope, but the DXFI we presented shows a left facing, so that's what I picked, was the left facing. Doesn't matter, it'd be exactly the same. And of course, this is the fill, the colluvium, and then the bedrock. So the fill, colluvium, bedrock. Okay, I did the non-reinforced analysis using the shear strengths that were given to us. And in the instructions, we were allowed to make some reasonable changes if we felt like that we needed to in what was presented, as long as we explained why we did it and what the modifications amounted to. And of course, this shows the groundwater and so forth. And so I got a factor of safety of 0.909, which is a little low for the back calculation, I thought. But anyway, let's talk about the modifications that I made. I made 3 modifications to the data that were provided. In the original data, the reinforcing bars in the upslope micropiles were 2 1/4 inch, and in the downslope were 1 3/4 inch. I assumed both bars to be the same at the 2 1/4 inch. And I kind of had a hint from some of the things I'd heard on it. So I made them the same, which seemed practical to me. Also, based on my initial analysis with the A-frames in place, I made the rock socket depths 19 feet into the bedrock for the upslope micropiles and 12 feet for the downslope, kind of assuming tension and compression is often assumed for those A-frames. The original depths were 25 feet and 15 feet. And the reason I based where I came up with the 12 and 19 was the depths based on the micropile load test capacities that would achieve a factor of safety in the static analysis of 1.5 minimum. And I only changed those depths in 1 foot increments. So I was a little below 1.5 or a little above, depending on what I made those lengths. And then one final thing on the modifications. When I was conducting the limit equilibrium search for the critical slip surface, I found that in the upper slope, up near the roadway, or whatever the structure was there, got a factor of safety of 0.8. Well, the information I had, that area hasn't failed. So that implied to me that the shear strength parameters of phi equals 22 degrees and C equals 0 are likely too low. Otherwise, we'd already have a failure up there. So I increased those parameters, iterated those until I got a factor of safety just a little above 1, because it hadn't failed yet. So I just reasoned that that would be appropriate. And that came up to 24 degrees plus 85 PSF cohesion. And I use those parameters throughout the remainder of my analyses. So here is the, you can see the slip surface there up at the top, and the factor of safety of 0.8 when I just let it search with those initial parameters. And then by increasing to the values that I gave you previously, iterating several runs, I got the factor of safety of 1.004 that indicated would be marginally stable. So I used those values. And then I ran it again for the unreinforced case, and I got a factor of safety 1.08. Now it's failing, it's creeping based on the inclinometers and so forth. So with a creeping slope, rather than a catastrophic failure to start with, we would expect the factor of safety to be a little above 1. And in fact, George Sowers I talked to him a lot about this, and he has some indication of it in his book. So we could remember that's factor of safety 1.08. And so if we consider that, normally if the stress ratio, which would be the mobilized stress divided by the available strength, mobilized shear stress, if that gets above about 70% or 0.7, we can expect probably some noticeable movements in the slope to occur. And the stress ratio is a reciprocal of factor of safety. And so when it reaches about 90% or greater, then we can see an accelerated, more rapid deformations in the slope that will be very obvious and over time can lead to a catastrophic failure. And so that means you've got a factor of safety of 1.1 or less when you have that condition, when it reaches about 90% or so. And so typically in discussions with George and my observations over time, that is usually about 1.05 to 1.1 is in that range. And if you notice the 1.08 I got, it's certainly in that range. All right, so going on to the reinforced analysis with the A-frames, I got a limit equilibrium factor of safety. This is all 2D right now. Limit equilibrium factor of safety of 1.565. And when I shortened up the micropiles in even or whole feet increments, I got a little below 1.5, so I went with this one. Then after, so this met the criteria, and then I ran 3D analysis with the limit equilibrium, and it was analyzed for the static case. Later on, I got some increase in or some analysis for seismic analysis for displacement. So I assumed two different lengths along the slope, L over D ratio, which L is the length of the failure surface, failure mass in the out of plane direction, and D is the depth, which I assume is the difference in the ends of the slip surface vertically. And so then I did a 5.81, which is equal to the 500-foot length of micropile beam. So I analyzed both of them. That's an input you have to input in the program by judgment. Everything else is calculated. Okay, so with that simplified 3D analysis, and by simplified, I mean it's the extruded section. In other words, it assumes that in the length that you assume, the stratigraphy is the same. If you go further along, you find the stratigraphy changes. It doesn't take that into account. You have to do another cross section at that point to analyze it in 3D. So I got factor of safety with L over D of 2, about 172 feet long, of 1.722, which is greater than 10%, is 10% greater than the 2D analysis. And then with L over D equal 5.8, 500 feet, I get a factor of safety 1.620, which is about 3.5% greater than the 2D. And we don't have time here to talk about it, but there's not a direct correspondence with safety analysis or strength reduction between 2D and 3D. So, but looking at those values, that gives a significant comfort level with our 2D analysis. In other words, we say, really got a 3D problem here, and the factors of safety are on up there, so it gives some comfort level with the 2D analysis. So then, in accordance with instructions, we analyzed for a PGA of 0.7, and that's probably the bedrock PGA, but we don't have enough information to amplify it up through the slope and all those kind of things. So, and typically, like according to Bill Marcuson and those guys, we probably ought to use a case of H, horizontal coefficient of about 1/3 to 1/2 of the PGA. Well, even 1/2 of the PGA here would give us a 0.035. And really, I don't know of anything that ought to be analyzed in the US less than 0.05 for pseudostatic anymore. So I use 0.05 for that. Notice on the bottom down there. All right, so I got a 1.286, which the criteria should be 1.1 or greater for this method. And then the other instruction was to use a 0.35 PGA, which gives us, using the 0.5 PGA, I used a case of H of 0.14, which is 40% of the PGA. And so now drop below 1.1 on the pseudostatic factor of safety, but still above 1. And then I ran a search for the KY value, the yield coefficient. That's using Newmark's method, which I'll talk about in a moment. You need the yield coefficient, which you can get from limited equilibrium. And that's the yield coefficient at which the factor of safety is 1. And the slip surface it yields at quite often is not the same as the surface with the lowest factor of safety. But anyway, that's what I got, something over 1. And this makes sense because the factor of safety of 0.14 was higher than 1. Okay, now if we go into the 2D finite element analysis, and the other two presenters use 3D numerical methods which can capture the response of the A-frame much better and so forth than the 2D, but the 2D is a good indication of what's going on. So this is a general deformation pattern. I think it was from my first analysis, but all of the deformation patterns were similar, just different magnitudes and so forth. So that shows, and this one is scaled up 300 times. You can see there. All right. So with a static deformation analysis, no horizontal coefficient applied, then I got less than a 1/2 inch of movement in the entire slope system. And the structural utilization ratio was less than 1, which means it's stable. We didn't use up all of the moment or the shear capacity, but it was getting on up there. So then I did the pseudostatic analysis. This is a static factor of safety doing Plaxis calls it safety analysis. Strength reduction is what it is. And I got a 1.545, very similar slip surface, and it matches up real well with the 1.565 I got with limit equilibrium. Then I went to the PGA of 0.07, case of H equal 0.05. Still, the deformation was less than a ½ inch, but the structural utilization ratio was somewhat over 1, which means that it's unstable. I think not by a great deal, but unstable. And the safety analysis was 1.235. All right, and then I went to the PGA of 0.35, and I couldn't get up to 1.14 for my case of H because anything above 0.1 collapsed looking at the iterations at about between 80 and 90% of the load, the system collapsed. So I couldn't get above case of H of 0.1, so remember that. Delta then became 26 inches, and the structural utilization ratio is considerably above 1, and so it's highly unstable. All right, and I did the safety analysis on that, and you'll notice the factor of safety, pseudostatic factor of safety is still above 1.1. That would show that it's okay. Just using pseudostatic analysis, which you cannot do, in my opinion. You've got to address the deformation because either one might be unacceptable if the other one is acceptable. So, and that's at a case of H of 0.1. So summarizing it in a table, initial condition with the shear strength phi equal 22 degrees plus 0 C, I got the 0.909, which I felt like was kind of too low. Then the upper slope, get the 0.8 factor of safety. Upper slope with increased phi of 24 plus 85 cohesion, I get the 1.004 like I presented earlier. And then with the micropiles, and this WMP just means with micropiles to shorten it up, and the 0.07, case of H 0.05, I got a little above 2, good agreement between the limit equilibrium and finite element method, but the displacement was, and the displacement was still acceptable, less than a ½ inch on the 0.07 PGA, but the system's unstable, a structural system. Then I went to the PGA 0.35, and there's not a direct comparison here because I could only use 0.1 in the FEM analysis, or the soil would collapse. So I got a factor of safety with limit equilibrium with 0.14, 1.022 compared to 1.138, but that's not a direct comparison because I couldn't raise the case of H any larger in the FEM. But the inches of displacement are 27 for limit equilibrium, 26 for the finite element. And the calculation of that's not really limit equilibrium. I have an option in the program to use Newmark's simplified method, which is not the full double integration of the ground motion for the sliding block. It's simplified equations that he presented in his 1965 Rankine lecture, where he showed you could use these equations to get the maximum probable displacement. And some of those criteria have changed since then, so it's an updated version of that. And so the system, the structural system, highly unstable. And for the seismic case of Y, where factor of safety equals 1 is 0.148 approximately. And so in conclusion, the limit equilibrium, finite element, and good agreement using the same size bars in upslope and downslope and increasing the phi and C for that shear strength. And then the calculated factor of safety was greater than 1.2. Displacements were very small, but the micropile system is unstable. Microsoft is too, but the calculated factor of safety is slightly above unity for the PGA equals 0.35 case, but the micropile system is highly unstable. And that's my presentation.
Thank you, Gary. I will say that let's hold our questions and comments till the end, and then we'll put everybody together. With that, I'll introduce our next speaker. It's Augusto Lucarelli with Itasca.
Thank you, Tim. Good morning, everybody. Okay, so here we have it. So we are going to talk about the same problem, starting with a brief introduction about the code and the modification that I applied to the problem itself. I took a slightly different approach. My background is in structural engineering, and then I find out that geotechnical engineering was more fun, and then combining the two is even more fun. And so you're going to see a lot of soil structural interaction with nonlinear structural element and advanced soil mechanics. Itasca is perceived as a software company, but in reality, 75% of our revenue is from consulting. The slides that you're seeing here are some of my projects, mostly related to ground improvement, soil stability, with different type of reinforcement and so on and so forth. For those of you that are interested, you can just go to the website, download the demo. It's fully functional, and it's the only limitation on the number of zone and number of elements that you can use. But anything else is working with all the options. So I'm not going to read all the details. The approach that I took is strength reduction, so you're not going to see or hear anything about limit equilibrium in this presentation. The strength reduction is nothing new, has been used for a long time. There are obviously pros and cons in any type of approach that we use. The most interesting aspect of this approach is that you can actually capture multiple mechanisms. You can consider in a more appropriate way the interaction and how the structure changes. Also the slip surface, the failure mechanism, and which one is failing first. Sometimes it's the structure that controls the behavior, sometimes is the ground itself that controls the behavior. And if we kind of always decouple the two systems, we may end up losing some of the components that may control the performance and the behavior of the system, like we are going to see in this particular example. There is a little bit of overlap. I didn't know what was the exact sequence. I'm going to skip on this slide because Tim already showed the general layout of the problem, so we don't need to focus too much. Just on the sketch, so the uphill micropile was 40 degrees, and the downhill micropile was 20 degrees. The focus of this presentation is really to try to capture the structural behavior of the frame system. What is the interaction with the capping beam, where the failure is likely to manifest in case we get up to there. So this is a slide that Tim didn't show. I think I'm going to spend just a second on this one because it shows how the bar or the micropile was organized. It is a composite system, so you see that the bar is going inside the capping beam. We have a bunch of plates, and then there is a casing that, of course, was used for drilling inside the colluvial. And then inside the rock, you don't need a casing, but there is only the grout. So the structural response of the system is governed by the weakest link that we have in the system. So casing is big and strong. You have a nice bending and shear capacity. The rebar is much, much smaller. And so if we compare the behavior of the three different systems, we need to consider all these different aspects combined together and how the casing influences the grout response and the rebar and so on and so forth. So the model that I put together was essentially a 3D model generated with different graphical tools. We are not going to get into the detail, but essentially each micropile is modeled independently. There are coupling springs that are connecting the micropiles with the continuum. All those coupling springs are doing, taking care of the interaction with the soil. And each micropile has all the members modeled explicitly from the grout to the rebar and the casing and all the plates. So if we go into the truss bending diagram of the different components, you see that the pink line is the casing. The rest of the curve are the rebar and the grout and also the shear behavior of the system. So I'm focusing on this truss bending behavior because we are used to think about that structure mostly in the axial term. But in reality, when we do the strength reduction, as Gary was showing in the 2D analysis, there is a lot of bending that will develop. And so the bending and shear, most of the time in this type of problem, is what controls the stability. In fact, when I implemented the problem, the axial force was not there, was a secondary aspect of the performance. Now, the capping beam, this seems to be, could be a little bit too extreme, but it's really not that difficult to implement this level of detail. So all the plates are included, the rebar inside the capping beam as well. So these are the steel rebar inside the capping beam, and also the nonlinear behavior of the concrete was considered in the analysis. Now, there was a load test on site. You can see that essentially there is a fairly linear behavior in the colluvial, as you would expect, and this is the bearing strata, the rock. I have assumed, here we can talk for probably an hour about this stuff, but essentially you have different options. The option, oops, sorry. The option that I tend to use is try to bracket the axial transfer, the load transfer, the bonding zone, because if we want to be conservative from the geotechnical side, we would tend to use less bonding zone, bond strength. But if you want to be conservative on the structural side, adopting a higher bond zone will give higher axial force and therefore more mobilization in the structural. So it depends on what we're looking to be conservative. And being conservative doesn't necessarily mean that you're conservative in one aspect and you're being conservative on the other aspect as well. So that's what I use for the analysis, 0.45 sigma prime V with a limit of 80 kPa in terms of bond strength for the casing, and then 6 sigma prime V less than 2,000 kilopascal. Sorry, I'm using SI unit. I'm still not familiar with the imperial system. And another aspect that is worth noticing is that the load test essentially is linear. We have not, those didn't show any geotechnical failure whatsoever. So we are fairly away from any type of failure. Now let's move on. The other liberty that I took is the adoption of a nonlinear strength for the soil. This is fairly common. Instead of kind of picking different strength parameter for different aspects or different location of the model, if we just adopt a nonlinear strength criteria like this one, you would not need to pick different angles or different cohesion depending on the slope angle, because the system takes care of itself. At low confinement, you have essentially higher tangent friction angle. At higher confinement, you have higher cohesion and lower friction angle. And essentially, the strength is updated as a function of the stress, of the normal stress that usually evolves during the analysis. So it's relatively easy to implement this type of strength in the software. And there were three triaxial tests that were done on remolded sample. So I'm kind of pushing the envelope. Obviously, the tests are not enough. We would need to do more tests. They were done on disturbed samples, but it gives you an idea about what is the trend in terms of strength that you have. And even if you don't have an example, you can still use, Tim Starr's correlations with error limits that are providing a very useful starting point to implement this type of approach. The other aspect that I was mentioning, I'm using in this approach, a peak, fully softened, and residual. And I'm using this term loosely just to give the idea that we have different level of strength that can be mobilized during the strength reduction process. So it's not really that the correct terminology, but I think we are all familiar with that anyway. The other aspect is deformability. If you can, try to get a shear wave velocity anytime because it gives you an idea about the small strain behavior of the soil. And when you do a soil structural interaction, especially in urban area, like Kim was showing earlier, it's quite important to be able to capture the initial part of the soil stiffness and how that would degrade with deformation. Then I implemented a very simple equation to evaluate the G over G max curve using Darren Daly's function, which are readily available. Now, the modeling approach. So this shows the full 3D model, and our section is the pink one, the one that was instrumented. It's fairly common and easy to build just the full 3D model and just cut a section like we are going to see in the next slide, and concentrate on the section that you need to start with the analysis, also for optimizing different type of structural layout. You see these 3 lines are essentially the inclinometers that were installed. It's also convenient and easy to kind of get rid of each other's slides and run 2, 3, 4 slides at the same time in the same model without any. It's a little bit slower, but not so much. Now, the first step is obviously to analyze the 2D condition, there is this terminology 2.5D condition. I never understood what that means, but essentially it means is that an extrusion in 2D for the geotechnical aspect, while the structural are modeled considering the spacing. So essentially, we have a structure that repeats itself with a certain interacts, and that is the thickness of our slice, essentially. So we capture the 3D local interaction of the pile or whatever the structural element is, but we keep a 2D plane strain condition for our geotechnical analysis. So the starting point, obviously, you have to initialize the stress in the model. When the fill was placed, initially everything was stable, and then for some reason, it started moving. It could be creep, it could be other local condition that might have manifested. So the strength reduction, the strength reduction starts from this red line, and then it goes down to this kind of a red-blue line. And what I'm showing here is essentially similar to the ground reaction curve of a tunnel. When you dig a tunnel, you get relaxation, and if you plot the pressure of the tunnel against the displacement of the wall, you get something similar. This is the same concept. You can do this with slope stability, with foundation, with anything that you are designing. I think is a convenient way to summarize and try to capture the different response of the slope that we are trying to analyze. You see that there is a fairly linear initial behavior where we keep reducing the strength from A06 to 0.5 something, and then we have this shoot. The system becomes unstable with these 2 lines. I've considered that's the starting point in which we install the micropile. So from that point on, we install the micropile, and we repeat the exercise. Now keep reducing the strength with this support installed. So our starting point for the analysis is this one, essentially. Before the system becomes completely unstable, we install the micropile, the capping beam, and everything else, and we keep reducing the strength. Now what we see is a different response of the system. In particular, this was the line without support that at that point was kind of going through the roof. And the red line is this average displacement of the failing zone with the micropiles. So we see that there is a translation on the right, and that is essentially the response, the structural stiffness contribution and strength contribution to the system. You see that there is also a deformed shape. you see that there is also a local mechanism here that is developing because the beam is modeled explicitly and the soil pushing against the beam is forming essentially a passive wedge, which limits the force that you can transfer actually to, because once you have reached passive resistance, that's the upper limit that you can get. So this is just a detail of the potential passive wedge that would form. The bending failure, then how the system would fail. Obviously, in this case, we're going to get into more detail a little bit later, but you see that there is a bend forming inside the capping beam. That is the connection of the plate and the rebar. So the kinematic of the capping beam, the rotation, imposes too much stress, theoretically, to the connection of the plate and the rebar. So once the rebar fails inside the capping beam, we don't have enough transfer with the casing, and then the system becomes essentially liable, like having an hinge connection instead of having a fixed connection at that point, and you lose significant amount of stiffness. It could still be stable theoretically, but the amount of displacement would increase so much that you would go out of service limit state. So this is the detail that I was talking earlier. Now, this is supposed to be a movie, and I don't know how to start. Oops. I was working? Oh, gosh.
Thanks for helping back there. So, can you
Okay.
go back to the slide? There you go.
Yeah, can you get...
Some help back there.
So as you see, this is the strength reduction process. You see the initiation and the red curve that are plotted. You don't really see anything happening until you are fairly high, and then the shoot up happen kind of dramatically. Once the break of the, let's say, internal rebar inside the beam are producing this change in the structural organization, essentially. So that's what I've seen in multiple times in this type of situation. Now, I tried, just for curiosity, a different layout. In particular, increase the inclination more to an anchor of the uphill row to see if that would increase. In fact, it would increase a little bit, but now we have the failure in the downhill micropile. So somewhere in between these two angles, there could be a sweet spot of inclination of the micropile that could reduce this kinematic pernicious behavior of the capping beam that controls the behavior. I didn't have the chance to play around too much, but just to give you the idea that this level of detail is essentially controlling the response of the system and is often neglected. Now let's go to the 3D. It's essentially the same concept. You start with initializing the model. You reduce the strength, like we see here. You get the failure in 3D condition. Slightly less strength reduction is necessary in 3D condition because the volume is not exactly an extrusion, so the thickness of the fill is variable along the progression of the project, but essentially is the same behavior. So that is the starting point for the installation of the micropile. And then when we install the micropile, we monitor the moving slides, and we get a very similar response with the shooting. And then this is the deform shape. You see that there are several hinges that are forming inside the micropile. Again, axial is not even invoked. I could have probably embedded half of the length inside the bedrock, save probably some money there, and maybe try to improve the detail up here because you see really the kink there of the bar that is changing and is not capable of transferring moment anymore. And then at that point, obviously, you lose and the system keeps moving and you keep producing bending and hinges along the structure. I look at the capping beam. Obviously, the capping beam needs to have a certain size because you need to have room to host all these plates, connection, and stuff like that. And it's not a surprise that the stress in the capping beam is very low from a concrete perspective, so is underutilized. And also the stress in the rebars is very low. This is we considering the total failure of the geotechnical side, the capping beam is perfectly functional. I don't know if I have anything else. Well, yeah, just a little bit of a summary. So the A-frame micropie structure is a relatively common type of approach to slope stabilization. Is actually quite effective. We need to pay a little bit more attention on the detail. This is a message that I would like to, it's okay to adopt simplified methods to have an initial idea, but really the configuration of the structure from inclination, connection to capping beams, how many level of micropile and how they are placed is playing an important role in the response. There is probably too much attention toward the axial capacity of the system, but very often is really the bending and the shear that is controlling the failure in this mechanism. And a final comment about the factor of safety. We are so used to just consider one number. We want this magic number, but there is more nuance to it. We should probably try to pay attention more to the full range of displacement. With the strength reduction, we can capture service limit state and how the system evolves and what are the failure mechanisms that are contributing to the different performance. And with that, I'm done. Thank you for your attention.
Excellent. Thank you, Augusto. I will introduce our next speakers, Jeff and Sina with Rock Science. And gentlemen, take it over.
Good morning, or howdy. So I'm going to go first, and then Sina's going to go after. I'm going to start with a quick introduction of just who we are, what we do, and we'll go into the problem. We're not going to have to introduce the problem as much because we're lucky to have Gary and Augusto go ahead and introduce the problem for us. So just going to speak a little bit about our company. So we've been around since the early 90s. We've been producing 2D and 3D software for geotechnical and civil engineers. We've got over 10,000 users around the world. And in North America, we have about 90 universities who use our software for teaching purposes. So that's something we're very proud of. We also take on about, I think this year we had about 20 co-op students. So they're starting to, sometimes at lunchtime, they kind of outnumber us. It's getting a little bit scary. But we have 80 people at our company. And our headquarters is here in Toronto, Canada. We're still kind of doing the hybrid. And if you notice in this, whoops, wrong button. Let me just go back to the laser. Yeah, so if you ever get a chance to visit Toronto, like we're friendly, like feel free to drop by, say hi. And so it's kind of like a B-list tourist attraction because people will stop by and they wonder what's happening with this building here. Why is it cut in half? And that's just because the development next door, the house, the owner couldn't decide. They couldn't agree on whether to sell the house or not. So they just did a very practical engineering type solution and just cut the house in half. So it's called the Half House in Toronto. So we do all of the development outside of Toronto, but we do have offices all over the world. Maybe one day we'll have a more permanent office in the States. We look forward to that. So we produce 18 different software programs. The newest one is Rockfall 3, which is a program for 3D rock slope analysis, and then also RSlog, which is a cloud-based borehole logging program. And that's partially why we have Sina and myself here, because there's a lot of programs to cover, so there's two of us at this presentation. But for today, we're going to focus on slide 2 here, which is our 2D limit equilibrium program. We've got slide 3, RS2, RS3, and then also RSpile. So we'll be showing you 4 programs. Slide 2 is a 2D limit equilibrium program that has a built-in finite element seepage module. It has a very powerful probabilistic engine inside, and also we have a very extensive library of supports. Slide 3 is the 3D version of slide 2. It has integration with radar data, and also you can bring in all sorts of 3D information directly into slide 3. So if you have drone data, LiDAR data, leapfrog data, you can bring them directly in. Next one would be RS2. So RS2 is our 2D finite element analysis program. It's very robust, so you can do all sorts of things with it, like soil stability, excavations, settlement, whatnot. RS3 is the 3D version of that. And then RSpile is our program for driven, lateral, axial pile analysis. It also does groups. It accounts for group effects. And it also integrates with slide 2. So the idea here is we try to make it easy for you guys. So if you're comfortable with using one method, you can very easily take your results, your model from one program to another without losing the geometry, without losing the soil properties, just to kind of reduce errors and a lot of extra work. So here we're going to show you how we've integrated, but we're passing data back between slide 2, slide 3, and then RS2, RS3. Eventually, with our borehole program, we'll be able to take your 3D borehole data and create 3D models out of that if you just even have borehole data and 3D surface data. So yeah, I'm not going to introduce the problem. It's been introduced a few times already, so I'm just going to talk about our workflow. So I'm going to start off by just showing how we analyze the problem using slide 2, RS2, and slide 3. We're going to obtain our baseline factor of safety, and then we're going to add our supports using the methods that you see here. So, so in step 2, we started off with RS2, where we assume that these piles are basically collapsed into a single plane, and we're looking at it in 2D, right? So we're smearing the effects of the pile into 2 dimensions. And then after that, we're going to show you how we took the pile forces that we got from RS2, and we apply them to slide 2 to get the factor of safety. We also actually took the displacement that we got from RS2, and then took that displacement, moved it to RSpile to get the pile forces, and then use those pile forces in the 2D linear equilibrium analysis. And then, and then the second last one there, we also took the RS2 forces and applied it to slide 3 for the pseudo, I guess, a 2.5D analysis. And then finally, we showed how we can actually do everything within just RS3, which is our 3D finite element program. You can model everything in true 3D and get your answer that way. So I started off running just RS2, and right away, when we did our first run, we noticed that the slope wanted to fail actually up here. And that's because this fill material that was given to us, it had a friction angle of 27 degrees. And the slope is actually at 35 degrees, right? So if you do your tan phi over tan alpha, you know right away you're not going to hit that factor of safety of even 1. You don't even have to run the analysis. You can find that it's unstable. And then we also noticed that in the fill material, the friction angle is 29 degrees. The slope is 22 degrees. So just based off of that, we knew that the target factor of safety of 1.5, that was impossible, because if you do 10, 22 over 29, you get 0.7 roughly. So we realized we have to just focus in the colluvium material. So our analysis is based off of that. And we set our search limit in finite element to tell the program to only run that one zone. And we got a factor of safety, or a SSR number of 0.92. So we know it is unstable. And even if you look at the shape of the failure here, it has good agreement with the inclinometer data that was given. So that helped reassure us that we're satisfied with that result. And we actually noticed that there is also another failure zone starting to develop here. We got our total displacement for the slope. So we saw that the slope wanted to deform about a foot with those strengths. And then we also ran it in slide 2. In slide 2, once again, we had to focus on just this area here. So we set our slope limits. And when we've also first started running slide 2, we have a new feature called MMO, and it's able to actually tell you that in one shot that this area here is unstable, the fill here is unstable, and then also globally is unstable. So you can do all of that at once now without running both a local and a global type of analysis. We took the 2D results and we extruded it into 3D just to check some of the 3D effects. So this is a pseudo analysis, right? Because we're just extruding it, and we got a slightly higher factor of safety, as you would expect from 3D, just due to the 3D effects. And then we also did the analysis using RS3, which is our 3D finite element program, to see if we can get the displacement contours to match up. So once again, we're getting a similar factor of safety, a similar failure shape. And then we looked at the total displacement, which has good agreement with the 2D case. And you'll notice if you compare the 3D displacement and the 2D displacement, there is some difference. And that difference is mainly just due to the different SSR number that we have there. So if you notice that in your analysis and you want the deformation to match up, you have to check to make sure you're using the same SSR. So our baseline results prior to putting in the supports, they're all under 1. And Stina will show you how we got to the target factor of safety of 1.5.
Okay, thank you, Jeff. Where can I go next?
Advance is green and then backwards is red.
Okay. Okay, as Jeff explained, we got the factor of safety of 0.9 something. One thing that I need to explain here is you expect that slide 3 and RS3, they should get the same answer, similar to slide 2 and RS2. The thing is, slide 3 is extruded with a large extrusion depths, the default by the software. But in the RS3 model, even for the reinforced one, we assume the plane strain condition, which means that the model is thin enough to ignore the displacement normal to the plane of the model. So that's a slight difference between RS3 and slide 3. Otherwise, they should give the same answer. For the pile analysis, so we used a couple of options in RS2. We had a couple of assumptions. I'm going to explain why we had these assumptions. This is for the cab. We used the linear option for the cab. As you see, the linear is elastic. So our focus was to get the target factor of safety of 1.5. So we assume that we don't want the cap and the piles fail. That's why we assume that they're elastic in the analysis. However, I'll show you how to compare the results with the allowable values. Then for the pile, we use the new feature that we have in RS2 called pile option. We used to use a structural interface. There is a slight difference between them. If you want, I'll explain later in the question section. But for the pile option, we have the out-of-plane spacing of 10 feet. As Jeff explained, the 2D analysis assumes that the piles are all in the same plane because it's 2D. And that with 10 feet of out-of-plane spacing. And for upper slope pile and lower slope pile, down slope pile, we defined the same way. Here is the results for the pile analysis. We had one small assumption here. For the fill material, we assume that the fill material is elastic. Jeff explained that because this is a purely frictional material, factor of safety cannot go larger than 1.37 because the slope angle and the value of the friction angle, the ratio cannot go over 1.37, and the failure is down the pile, so you can't see the effect of a pile. So we assume that we kind of stabilize the fill material, that the failure doesn't happen in the fill material. With that assumption, we got this failure surface that it's going to the Clovian material. and with a factor of safety of 1.64. Again, we assume that the piles are not failing, but you can get the axial forces, like here, the shear forces in piles, and also the moments. So you can get all these informations and compare with the allowable values. And this is the total displacement for the whole model, which is the maximum is 1 feet, and for the piles as well. Then I would assume that a lot of people here expect that we start with RSpile slide integration. We do RSpile, and this is actually what we were asked for, to do RSpile and then a slide. But something that you should know about RSpile and slide integration, I'll show you in the next slide how it's gonna work. But the thing is, when you apply a 1-inch displacement to the cap, and you can't expect those two battered piles to behave the same way. But a slide and RSpile integration, the assumption is you apply allowable displacement in a slide, take it to RSpile, get the reactions, bring it back to a slide. But when they pile group, they behave differently, each pile. You can't just bring them one by one. It's a manual process. So instead of doing that, we started with RS2. We got the shear and axial forces in RS2, and we brought those values into a slide. We didn't use the pile option, we used the tieback option, and the reason for that, if you want to look at the axial and shear forces, the under reactions, like the one pile is in compression, the other one is in tension, you should use tieback, because in tieback you can assume shear, you can assume tension, compression, and this is what we did. Shear controlled the results. You can see that the shear values are there. And factor of safety was 1.6 based on the values that we imported from RS2. Then, since we wanted really to do RSpile, we got the displacement profile for the critical slip surface location in RS2. And you can see two displacement for two different piles. And the vertical line is because that's below the critical slip surface, so we ignore that part. We assume just the displacement is above the failure surface. And we apply to the piles in the RSpile analysis. We got the pile reactions, shear forces, you can see the numbers for lower pile and upper pile. And then for this case, we use the micropile option in a slide. So we got the reactions in RSpile analysis, and we brought them to a slide and calculated factor of safety, and it's 1.6 again, very similar to what we had. So the reason for that is we started from RS2 and we brought the values from RS2, and there is no reason that limit equilibrium and finite element can get the same answer here. Next, we use the reactions that we got from RS2 in the slide 3 analysis, but with the correct arrangements of the piles. They are not in one plane anymore. One of them, like every other one, is battered 40 and 20, and with the 5 feet spacing between each of those. And we got the factor of safety of 1.68. which is typical value for 3D analysis to give higher than 2D analysis, and makes sense. And these are the reactions for the piles. Again, these are tiebacks, and we have both axial and shear, and you can see, I don't think it's too small, but shear values are controlling the results. And then we said, okay, forget about everything. Now let's start fresh and do RS3. In RS3, you don't have to use any of these RS2 results. It has its own cap analysis. You can define the cap using linear surfaces. You can define the pile using the pile option. And that's what we did. But again, this is the plane strain condition, because factor of safety might be higher than the 2D analysis, but we wanted to match RS2 and RS3. So this is a plane strain condition, failure surface is the same, and this is the shear strength reduction method, which is 1.6. Now, in RS3, these are the actual forces, because the arrangements of the piles are correct. This is a 3D analysis, so you can look at axial, shear, and moment graphs for each pile. These are the contours for each pile at different locations. This is the cap. So for cap, you can see shear at different orientations. You can see different moments, mx and my. And you can look at the total displacement as well for the whole model, for the piles, and for the cap in the RS3 model. And this is the final table of our outputs. So baseline, as we mentioned, factor of safety of 0.9, with the assumptions that I explained, and with supports, using a slide 2, RS2, a slide 3, and RS3, factors of safeties are very similar, except a slide 3, because again, it's extruded for, I think, 400 or 500 feet, I don't remember really. Factor of safety is slightly higher because you see the actual 3D action. And with that,
thank you, Jeff and Sina. All right, so now we'll transition into our discussion period. If it's okay, can I just pull this mic down? And we've got another mic. Can they both stay live, or do you want us to? They're alive. Okay. So yeah, Ed, if you could help. Oh, there we go. Thanks. All right. So if you have a question for all our panel or one person, if you would just raise your hand, and you kind of cover that side. I'll cover this side, if that's okay.
I'll start with the defense of Tim. So just for background, when Tim provided us this problem, and then we took and stripped out a lot of relevant information, made up the parameters, and then when you saw Dr. Gregory do some seismic, we said, if you've got time, could you do a seismic screening analysis? And then we've made up those parameters. So when you see it deflected 26 inches and all that stuff, that's not what Tim's project had.
I kind of said it a different way. Augusto called me and told me some of the problems with our design, and I said, thank you, Augusto, for calling our baby ugly. So that's fine. So ask away.
I'll send this question out to the panel, but if anybody in the room has a comment that helps after they get a chance, I'd love to hear the response on this. So there's a lot of study in the models, particularly structurally in the micropiles and the moments that exist, and the discussion about the shear and the combined stresses that control the failure in the piles. What I haven't heard discussed would be the limiting moment that would occur at casing joints, and how the casing joints will play into the locations along those piles. The 3D models should do a really good job of showing where the high moments were existing. How would that work with constructability, 20-foot sections, 10-foot sections, 5-foot sections, any casing restrictions? Augusto mentioned the two different cross sections with the bar at the rock, and so on. So if you guys can comment a little bit on that, I'd love to hear it. Thank you.
Yeah, I believe I'm going to start. So first of all, I didn't call Tim to say that this project. I said, with this example, I see this potential issue. So just to clarify, there is nothing wrong. The wall is sitting there, is performing nicely, and whatever the number in terms of safety factor is, everything is looking fine. So Tim,
thanks.
Everything is so going back to Mike's question, I wasn't able to convey the message clearly enough, but the organization of the 3D model actually capture the contribution of each component inside the system. I model explicitly the rebar, the grout, the casing where it's present, and everything is connected with, let's say, coupling springs that are taking care also potential sliding between the casing and the grout, or the bar and the grout and whatnot. So what emerges from the model is theoretically the natural response of the system. And where the failure would manifest is the weak link, where we are looking actually, which is in this case the connection of the rebar when it comes off from the top plate of the casing. That is the weak point. And we also shown that if we manage the inclination of the micropiles in such a way that the kinematic doesn't, let's say, insist only on uphill or downhill, but it kind of provides a more homogeneous type of displacement without too much rotation, that would be the sweet spot in terms of organizing the inclination of the system. So I'm not sure if this is answering your question.
Somewhat. I was really interested when I saw Cena's moment plot that had the high moments down at the slide plane. I was interested in whether you believe it to be critical, and if anybody investigated the reduced bending that would occur at a casing threaded joint section, and what value you may suggest for using it.
For this model, particularly, we did not, we used equivalent parameters for a beam. We did not look at the casing and stuff, but yes, we have these options in RS3 as well, that you can define the rebars and casings and stuff and look at specifically at those moments and plot them and see if they are critical or not. But again, these piles are very elastic as well, so you really can't. If you define the plastic, you can define different parameters and specifically look at different locations and see if those are the failures or not.
Mike, and I'll just make comment on our side. I think we typically would do one of two things. Either we would assume that the bending capacity all along the pile would be 50% to represent that the threads could occur anywhere. Or we would talk with a contractor, see if there's a way that they felt comfortable to improve the threaded connection. Anyway, I'm going to give it over to John.
I've worked on 2 of these micropile projects that have had over $100,000 worth of instrumentation on each one. And to follow up on what Tim just said, what we did in those locations, Mike, is we used upsize connections with 4.5-inch pipe, 0.35 wall that had 6-inch connections. They were upsized because you don't know where the maximum bending moment is going to be exactly. You know, we're not God. We can't see underground. And so the connections were the strongest part of our piles. And so then you don't have to worry about that.
Thank you, John.
I'll give a little bit of response here, and I agree with everything that was said, actually. You know, from a practical standpoint, we never have enough data. And so I think we have to be realistic in our analysis and apply appropriate factors of safety, whether it's to the structural system or to the geotechnical parameters. And I think in this case, all 3 of us recognize that the structural system was the weakest link overall. Everyone can speak for themselves, but that's what I gleaned from their analysis, certainly from mine. And I applied structural. I calculated outside the program the structural capacities, and I applied a factor of safety 1.6 to those. And so many times we're not sure what the exact details of construction will be for the structural elements. We're certainly not sure of the geotechnical parameters. They don't appear to be critical in this case, but in other cases they may be. And you know, considering the high variability of the subsurface parameters and the strengths and so forth that we know or don't know, then I think we always have to be realistic in our analysis. And it's like having a factor of safety to 3 decimal places. We'd be lucky to be accurate to 1, you know, because I mean, we think we know where the stratigraphy is, but I've been on many projects where we analyzed it, and after they got on the job site, the rock was 20 feet different in elevation in some locations than what was characterized. So I think when we're doing all this, we have to be totally realistic. And also, I think we have to apply and build this into our design, some people have indicated this, going back to Ralph Peck's observational method during construction, we never know the subsurface to the detail that sometimes we think we do, or that we hope we do. And so I think during construction, when those things change, we have to have designed a system coordinated with the owner or the prime consultant or whomever's in charge to be able to modify our design or our approach to it so that we can match our system to the ground as we find it during construction.
I do have a quick question. I kind of ask the same question every year. So with some of the models that were all different, but could you speak to what subsurface investigation you think is required in order to obtain the correct data to put into these models instead of just tables and whatnot? I think it's important to have a good investigation. So beyond just borings and stuff like that. So if you guys could maybe speak to that.
Yeah, I'm gonna start again. I don't rely on lab data pretty much for anything besides some shear strength. If you're doing a deformation analysis, lab data is probably, I would say, the worst source in terms of reliability because of scale effect, disturbance, and whatnot. There is a bunch of list of potential problems. I tend to rely on an in situ test, and probably shear wave velocity I mentioned during the presentation when you can try to get a shear wave velocity measurements. CPTs when it's possible on kind of a cone-head. So it really provides a very, very good source. And you can calibrate all the model, for example, the plastic hardening directly using CPTs and using the material index of solid behavioral type automatically. And I've been doing this in many situations before construction, before the job start, and the performance after with measurements and monitoring was quite good. So in situ test all the time.
I agree with Augusto. Some of the stress-dependent models that we'd use in the numerical analysis, finite element or finite difference, et cetera, have 10 or more parameters, soil parameters to be input. And probably at least 6 out of 10 are fairly critical. It'd be fairly sensitive to those. And as he mentioned, it's very difficult to get accurate results from lab tests because, first of all, we never have enough. And so the good quality field tests are really important. But when we run a stress-dependent model, hardening soil model or, whatever the model is, you're familiar with those. I have to realize that I had an advisor once that had a good saying, and we all know the saying of a finite element model, garbage in, garbage out. He always said, that's not the problem. The problem is when people think it's garbage in, gospel out. and so we have to realize the limitations of the data that we have. And but one thing we can do, and it costs money to do this, but we need to do it if we're doing those kind of analysis. We certainly need to do parametric studies, sensitivity, so that, because once we have enough data, the limited amount that we have, you can use a better judgment on, fairly accurate judgment on what the lower bound and the upper bound is. And so then you can see how sensitive it is to those, that range. And also the parameters that really affect the results of the soil parameters for the more sophisticated model, you can try different ones within those, so it's an overall as well as changing those individual things parametrically and all. That takes a lot of effort, and all, but it can give some good results. And I think we ought to strive to get our clients in the boat with us. And I'm always saying, I don't mind to be in the boat that's being circled by sharks if my client is in there with me. But if they're up on the bank and I'm out in the boat circled by sharks, I'm uncomfortable. So getting them to buy into what we're doing and that there is a range that we need to consider, and then the risk is a whole different topic, but that's another thing. So we shouldn't overestimate the accuracy of the data we have and think because we're using a sophisticated model that we're getting the right answer if we don't have those data. And of course here, we're just taking the data we have and making the standard assumptions and all, but in the real problem, that's what you have to consider, I think.
And then
Okay,
just quick answer for this one. We agree with Augusto and Gary. You asked this question last year, I remember, and then I guess our response again this year is we're really good at taking your parameters and giving you that critical failure surface. We don't do the consulting part, and we don't have as much experience on the consulting end. So, I can tell you what we do like. We like running a back analysis. Like if we have anywhere on site where we see where there has been failure, there's been some indication of movement. We like to calibrate the model so that it performs similar to what you're seeing on site.
Okay, I have two questions. The first one, when we perform this kind of slope stability analysis with structure elements, like in this case you have the micropile, the soil and the structure elements, we should have different factor of safety, right? So based on all the presentation you guys performed, I didn't see anybody mention you come up 1.5, 1.6 for the slope, but what the factor of safety for structure elements you guys used? This is my first question. The second question is, if we perform numerical analysis to calculate the factor of safety, basically for me, the deformation is meaningless because we reduce the strength. The deformation is is not useful. So I saw you guys mention some deformation for shear strength reduction method. Does make sense or not?
I'm
not sure about the second question. Maybe we can come back. Let me try to tackle the first one, which was the safety or factor safety between the geotechnical and the structural component. It depends on the approach that you're using. If you're using an organic approach that combines everything in one model, you don't need to apply any factor safety in any of the components. So you're using, let's say, design properties. The factor safety emerges during the analysis. Like, for example, in my case, if you plot the displacement of a volume against the strength reduction number, you would see that at some point you observe instability. And that instability could be because it fails on the geotechnical side. That would be your factor safety in terms of geotechnical analysis, or it fails in the structural aspect. And you use, let's say, non-factor property for the structural aspect as well, because the response of the structure will develop and mobilize all the way up to the structural failure. So you get essentially both components, and you see what is the factor of safety that you get after. You do not impose it first.
So if I could, I guess to say it maybe a slightly different way, in your analysis, you put the limit strength of all components and calculated the factor safety of the system.
Yeah, or the component.
Well, it'll be the weak component, it'll be the controlling component that you get the factor safety.
Yeah.
The controlling component will be.
Yes. So when we perform the soil nail or tie back analysis, if you check the FHWA manual, they specify different factor safety for different elements. For bond strength, for tension,
whatever, they have different. So that case, we need to reduce your structure elements, like based on factor of safety that's specified in the manual, then perform the slope stability. That's what I understand.
What I did, I mentioned, but it probably wasn't real clear, but using that approach, and of course, we didn't have a lot of data. I had to do a lot of calculations outside the data we had, like for the structural capacities, the ultimate capacities of the structural elements. So I applied a factor of safety to all of those combined, 1.6. And of course, for the soil, just on the factor of safety basis, we were instructed that the target factor of safety is 1.5. That's a whole different topic of what that might need to be in a particular case, but that's what we were targeting here is a 1.5 for the static case. For the in the limit equilibrium with the extended Newmark simplified method in my software, I should, for it to pass the screening test, I would need a 1.1 on the seismic, and so that's what I was targeting for that, and I don't know if that answers your question, but and the different elements of the structural components could be factored differently, but because we had to make simplifying assumptions based on the data we didn't have, I just applied a 1.6 to
well, in addition, it really depends on which direction you're going. If you're designing and you can tolerate a different factor safety for different, like structurally, like soil nailing, you could count on a different factor safety for the nail versus the head connection versus the slide and back. That's one direction, but what this panelist was their goal was to take an existing design and evaluate it for the critical factor safety. And that could have been any component.
So when we perform the soil nail or tie back the bond strength, based on FHWA manual, the factor safety is 2, right? 2.0 for static case. So if you apply 1.5 or 1.6, that means you are not you are not performed in accordance with the manual. That's
just one simple note. If you want to analyze the bond strength in particular of soil nail, you just reduce the bond strength in your system. Okay, that's the only component. And if you get stability for factor or reduction factor above 2, you're okay. You do not apply the strength reduction factor or factor safety before doing a soil structural interaction because you compromise the response of the system. It makes no sense. What are you getting out of the model if you apply the factor safety before doing the analysis?
Are you talking, this is critically important, are you talking about limit equilibrium analysis or finite element? Or
both. For limited equilibrium method, if you use the slide, they have the function. You can reduce when you perform the stability, then you don't need to apply factor safety for your structure elements, or you have combined factor safety for both soil and structure elements. That's the slide analysis. Or slope W, they also have some kind of function. You can separate the factor safety.
Yeah,
I know the flag also have the function. You can run the shear strength reduction method, combine the factor safety, or separate it.
Yeah. Well, the factor of safety and limit equilibrium should not be, in my opinion, should not be applied to the reinforcing elements in the program. It ought to be applied prior to the program. And I think all of the commonly used limit equilibrium software give you the ability to, you have to put in the bond strength, the tendon strength, all of those things, and you factor all of those before you put it in for limit equilibrium. It's a totally different story if you're doing the strength reduction analysis in a numerical method. So it depends on which one you're talking about using, because it's two different two different things.
Yeah, I think in general, the problem was global stability goal was 1.5. We didn't really specify any other procedural type steps
Right,
after that.
right.
Okay.
Yeah, I mean, that's what the manuals have. Individual components having individual factors of safety. So,
Since you mentioned a slide, sorry, can I add something here? In a slide, so you're talking about a lot of different things. It's not just a limit equilibrium finite element. Basically, in limit equilibrium, the force that you are applying for your support is the maximum possible force. So you can go ultimate, you can go level. You have the ability to apply reduction factor to the ultimate strength that you have in your support separately for bond strength or anything you want. But I think what you're talking about is active and passive option as well, which you either apply the factor of safety during the, because factor of safety calculation in limit equilibrium is an iterative process. So you have the F on both sides, and you can apply your factor of safety at the same time to your supports as well. So what Gary said is correct. You can either do it beforehand and use the method that you don't apply any factor of safety, or you can just let the software during that iterative process to apply every single factor of safety to your support as well. One of them is more conservative, it gives a lower factor of safety. It's up to the user which one to use. But if you know the factor in advance, you should apply it first and use the method that you don't apply any factor of safety to your support. But in finite element, it's a totally different story. You don't apply anything, you define some capacity for your support. That capacity is being developed during the process of the numerical analysis. So the finite element mesh that you define is going to include your support properties as well at the nodes. And based on the development of your stress and strain, a part of that capacity is going to be in the calculation. So if you reach the ultimate capacity, your structure is going to fail, your support is going to fail. If soil is going to reach the ultimate capacity, your soil is going to fail. So it's a different story. Limit equilibrium is a totally different tool than finite element. About the deformation in the shear strength reduction method that you mentioned, we reduce the shear strength, but in the convergence process, because we do some iterative process to see if the model converges or not, over there, the strain is going to be calculated and compared in each step. So it's something, deformation is going to be considered there.
So once you reduce your factors, your stress becomes stress design. We cannot mention deformation during your, when you use stress design measurement.
I think we should discuss further because I don't exactly get what you're asking. So I'll show you something if you want.
So this is not a question. I wanted to share something with everyone. Some of you or most of you know that DFI has a podcast called Broadcasting Common Ground. And so the second series, which is called as DFI Rumble, the latest episode was on discussing skeptics versus modeler. So Augusto is on it, and Brian Anderson from Auburn University. I think you can guess who is a skeptic and who is the modeler here. So I would say listen to the episode. It's really great, and let us know what you think. There are a few of the things that they were discussing today is included in that episode. Brian here has listened to it already, so you can ask him how it is, and let us know what you think.
May I make a comment? I'm usually depicted like the believer, but I'm very skeptical. I just wanted to clarify that. No, because in the podcast there is the believer and the skeptical. So just want to make that clear.
So in this model, you guys are saying that axial load wasn't really as much of a problem as bending was. What I'm wondering is if that rock layer was a softer material, like an IGM or even softer than that, would you anticipate the whole system, obviously I would anticipate the whole system deflecting more, but as a result, would you anticipate bending, shifting from being the controlling to axial load more controlling in that case?
What I've seen is that really to trigger what you're saying, you need to have a bond failure in the compressive side, usually, which is the downhill. In tension, at least for the system that I have analyzed, they tend to mobilize later. But of course, it depends on the local condition, depends on the material. So I'm kind of extrapolating based off of my experience. If you have a bearing capacity failure for mobilization of the bond strength downhill, then you see what you are mentioning. Otherwise, in my experience, probably 90% or even more is always bending and shear that is controlling in this type of framework.
Yeah, I agree with that, that's one reason we have to analyze it, because as the rock socket gets shorter and shorter, then I think Augusto mentioned that for this problem, from a geotechnical standpoint, the sockets could be a lot shorter.
If
but
we believe to those data, according to the data that we have, theoretically it could be shorter.
Yeah, it could be shorter. And of course, if you do that, then at some point you could have an axial issue as well. But in this case, as he mentioned, it was a shearing moment. And of course, we've got it's micropile, fairly small diameter. But as I mentioned in my approach, I shortened the two proportionately till I got down to just comfortably above 1.5 in the limit equilibrium analysis. I found in my analyses that if it's a problem I can analyze with limit equilibrium to start with, it gives me a better idea what to go into the finite element analysis with, rather than not having as much idea and start there. All different approaches, and I think we came to the same conclusions overall here, exactly with our approach. But certainly that could be a problem, but it wasn't in this case. It was for the utilization was pretty small on axial capacity.
Augusto, you mentioned a lot about your findings. You illustrated the criticality of looking at that cap connection and that design. I'm curious if any of the other panelists found similar results or had the same takeaway of how critical that is in design.
I just used a plate. It's pretty small on the scale, but I just used a plate. And since I was doing 2D only, which I didn't initially, I was only going to do limit equilibrium, but because of one panel member couldn't make it, I decided to do the 2D finite element analysis. And so with the 2D, you don't really get the full picture of what's going on in the cap. And I didn't, due to time constraints and so forth, I didn't try to really analyze my results about where the different things were occurring in the cap. So I just did a simple calculation of the properties of that cap as a plate member and plugged it in that way. So what Augusto did and also Sina and Jeff was much more accurate on bringing out that information. But we all concluded that the problem was within the structural system, and of course that's because of the parameters we were using, not, as we said, not what they actually used in the design.
Yeah. On our side, the same. We did the 3D finite element analysis, but we didn't really look at the cap problems. But and we assume that it's elastic. So this is one stage of our work, and as a matter of fact, we're going to continue working on this problem because we're going to look at the plastic behavior, we're going to look at the moments, what are the problems, We use the equivalent properties for supports. As a beam, we're going to use reinforced concrete. We want to investigate this more on our side because, and especially with RS3, because it's a general tree-defined element and we can get all this information. And we normally publish this kind of work in different DFI conferences actually. Whatever we have done at S3, we publish at General next year. So definitely check for it. You're gonna see a lot of things out of this.
I guess just if I can make a final comment. I work a lot in litigation, so I have the mindset of finding the proverbial devils into the details, and so that was the mindset that I adopted here. So.
Yeah, let's kind of wrap up with a final statement. I'm gonna, if it's okay, I'll start. I think my big takeaway. So when we first did this design, we did 3 levels. So we did a hand calculations, and we're fortunate enough to have John Turner, who works with us, who has used a hand calculation for many, many years in solving these problems. And in fact, I think he worked on a good bit of John's projects back in the day before we had some of these high-level numerical analysis. We also did a limit equilibrium because we didn't really believe our hand calculations, to 100%. And then we didn't believe our limit equilibrium either to 100%. So we did a numerical model using Rock Science's software, and we didn't believe that to 100%. I think our takeaway is I believe we didn't believe any of it to the extent that we put in inclinometers to see what the post performance would be. And my recollection is that we saw a little bit of movement early on, but we got about 1 inch, which tied in well with Gary's calculation, at which point we kind of breathed a sigh of relief. I mean, to be honest with you, because we were really, I think from a design side, we were going from a factor safety about 1, and we were targeting, I believe, about 1.3. But, remember, this side slope it's craggy rock, it's deep colluvium next to a lake. So there's a lot of uncertainty in this, I mean, we collected data, but it's not easy to collect data in that stuff. And really, I don't think anybody's solved the problem of really getting an accurate strength of colluvium because, we can back calculate, we really can't get a great sample of it. But moving on, I think the conclusion that we came through is that this was a nice exercise. I think everybody kind of came up with the same conclusion that the factor of safety globally was, certainly greater than 1.3, but maybe 1.5, and that we didn't really overstress some of the structure, which is always the concern when we've got this composite system. I will say that, and I kind of jokingly said that with Augusto, but he did identify an issue, and this is great about the numerical model, is that because it lets you look at kind of the whole picture, what he focused in was a localized issue, which was the passive wedge on the upside of the cap. And I'm going to be honest with you, that's not something that we would, and I think we did check that with hand calculation, but we certainly didn't do it with limit equilibrium. And I think even our numerical model would, we probably limited some of the failure surfaces to try to create something more realistic. But we probably didn't have certainly the 1.5 was kind of a device for this effort. But, that's something beautiful that the numerical model can show you is saying, okay, if that resistance is really dependent on that passive wedge developing and you're limited to that, you may not see it if you just make some assumption. And anyway, so that's my concluding remark. Gary?
If I just interrupt real quick, since you made that passive statement.
Yeah.
That's been identified on some of these big projects, and we've had to put in short micropiles uphill on some of these caps to try to give us a more of like a soil nail deep foundation problem. But that's exactly what has happened on some of those projects, and it can be fixed by that.
And I don't think, and I believe we checked it, but we didn't look for factor safety 1.5. But Augusto picked up on it very quickly. He goes, I'm never going to be able to get a 1.5 because,
That really happens.
but now here's a question for you. And let's maybe go back to this other comment. Do we really need a factor safety 1.5 for that uphill wedge? We almost have a pretty good control of that, right? You with me?
Yeah, totally.
I mean, you got it. I mean, it could have been as simple as excavating out and put gravel back there, and that would have bumped you up. But anyway, Gary, your final comment?
Yeah, one of the things that I think is illustrated in this exercise is deterministic factors of safety and limit equilibrium. The limit equilibrium is a fantastic tool. It's proven to be very good over the years for many things. It can't get the final answer in most cases for a soil structure interaction problem. You know, some of the factors of safety, 1.5, whatever, that have been developed over the years has shown that if you adhere to some of those factor safety guidelines, you're probably going to be okay in a lot of cases with the overall performance when you have structural elements involved. So it's very useful, but it's not the complete answer. And, you know, I've seen situations where people say, you know, should we use finite element or numerical methods with strength reduction or whatever? Well, use them both, because you can easily see here factors of safety that were achieved with that were acceptable, and especially in the pseudostatic seismic analysis, were above what we normally see, but the system wasn't, as we analyzed it with the parameters, wasn't adequate. And so for a complete, as much as we can do anything complete, you need the numerical methods for the final answer in soil structure interaction. You just can't get there with limit equilibrium, although it's a real good start sometimes.
Augusto, you?
Well, I mean, I guess I probably am going to repeat myself, and I'm going to keep it short. I agree with everything that was exposed. I struggle to just embrace the idea that we need to rely on one number. It doesn't really give the picture. I would encourage to adopt a more comprehensive approach and look at deformation, because there is a stress-strain relationship that we have to deal with. We can't just look at stress. Deformation are controlling pretty much the response, and sometimes even more important than the stress, because they're controlling the stress dependent or strain dependent and everything else in terms of response, structural mobilization. And not all the system is getting to the failure point with the same rate and at the same time. It depends on the relative stiffness of the different component, which one is going to get there first. And we probably need to make a little bit more effort to try to summarize. Just creating a picture of strength reduction against displacement or force or reaction of a component, and you put that in a plot, you have an immediate picture of what is the controlling factor right away. That's my comment.
Super. Jeff? Or Sina, or both?
Let me comment on a couple of things. I'll be quick. About the difference between limit equilibrium and finite element, it's too soon for the practice to switch to finite element like as a unique answer. A lot of people, very high percentage of our customers, they are still using circular Bishop method. So you can't expect that that level of expertise goes directly to finite element. But we teach these in our courses that limit equilibrium, like 90% of the cases, you should get the same answer in finite element. But when the structural elements, they come into the account, you have to have a lot of simplifications to match the results of finite element and limit equilibrium. So for this problem specifically, we show that they match, but really we did a lot of efforts on the finite element side to match the limit equilibrium part. So if you want for this kind of analysis to get better answer, to get real answer, you should go directly to finite element. But you should get the expertise. You can't just assume numbers. You can't just assume constitutive model parameters. You can't just assume like the elements, how you define them. So I think what we are trying to do is to show that limit equilibrium is still able to do that, but we need to educate ourselves to do numerical analysis as well. We have RSpile, which is a numerical software. it does based on the 3D finite element analysis of the piles. That's why we integrated it with slide and slide 3, at least to help to fill this gap, because you do the numerical analysis by assuming your piles and analyzing with a numerical model, and then bring whatever you have into limit equilibrium analysis instead of just assuming a constant shear for your piles, which is not really the case. So I hope we showed you some useful information.
Very good. I want to reiterate, or at least acknowledge, these panelists spent hours, probably days, working on this problem. So if you don't mind, let's thank them again for their effort.